Okay, now we're on the second part of the lecture. In this part, I'm going to be presenting AirLift. So AirLift is a fast and comprehensive technique for remapping alignments between reference genomes. This work was co-led by Jeremy and me. So I already covered some background slides on genome analysis, so I'll relatively go over these slides relatively quickly. We know that genome analysis is critical for many applications such as personalized medicine, outbreak tracing, and evolutionary studies, and we know that DNA sequencing machines generate fragmented sequences known as reads. And we already covered that those reads actually can be mapped to their reference genome to identify the potential mapping locations and also the differences between a read and the reference genome. And probably from the previous part of today's lecture, you already inferred that the reference genome should be accurate and complete so that we can enable accurate analysis in the later steps of genome analysis, for example, variant calling or gene annotation and enrichment. If it isn't, so if you imagine that the reference genome is inaccurate or incomplete, then this essentially means that we're not mapping our reads to their correct origins, or we're not mapping them at all. So that's why it is important to do so. And to achieve the best accuracy and best completeness in the reference genomes, these reference genomes are usually updated regularly to their new versions, the updated versions of the reference genome. And such an update could resolve some unknown regions in the old reference genome by figuring out what sort of sequences should come to these unknown regions in the old reference genome, or by correcting the errors in the older versions. So remapping the reads to the updated reference genome can generate novel information because we can now more accurately identify the genomic differences in case there was some inaccuracy in the old reference genome, right? And we can now also map the previously unmapped reads to the new reference genome in case we're filling in the missing genomic sequences in the new reference genome, or by correcting the potential errors that were present in the old reference genome, but they no longer present in the new reference genome. So I'll quickly go over the potential changes that can exist between two reference genomes. In this case, we have old and the new reference genomes, and we identify 4 particular regions here, as we label with different colors: constant, updated, retired, and new regions, as we show also in this figure. So the retired regions would mean that the region is completely removed from the new reference genome. It no longer exists. The new region would mean that this particular region is completely novel in the new reference genome. So this is a new addition that didn't exist in the old reference genome. So we also have some constant regions that are exactly the same between the old reference and the new reference genome. However, their positions may still change. As we try to illustrate here, this particular exactly matching region is slightly shifted towards left in the new reference genome due to potentially the retired and the new regions between old reference genome. So we may have these shifts because we have these insertions and deletions between new and old reference genome. And we also have some updated regions. So we label them as updated regions because they are mostly the same sequences between two reference genomes, but there are still like slight changes, small changes between these two reference genomes. So you can assume that these bars over there are these slight changes between reference genomes. And whenever there's a new reference genome, we want to basically utilize the new and hopefully more accurate information we have there. And this is usually done by remapping the reads from an old reference genome to the new one. And there are usually 2 solutions to achieve that. And the first solution is to map all the reads from scratch to the new reference genome without utilizing whatever information we have in the old reference genome mapping. And the second is to utilize some information that we have in the old reference genome mapping, and then move the mappings to their corresponding locations in the new reference genome without mapping all the reads from scratch. So I'll go over the first solution now. So you can assume that there may be some mapped reads to the old reference genome, right? And what we do is that we collect all these reads, and as well as all other reads that were previously unmapped to the old reference genome, and then take all of these reads and then use some read mapping tools such as BWA, Minimap2, and then map them again to a new reference genome. So this is essentially a very accurate mapping, because what we're basically doing is that we're mapping the entire set of reads from scratch to the new reference genome. However, this causes a significant computation overhead, and this is why. So you can assume that this is the entire reference genome, and however, when we're updating the reference genomes, and when we're moving from old to new reference genome, what we see is that usually a 12% of the new reference genome is different than the new reference genome, or vice versa. So this means that a large portion of the reference genome remains unchanged, meaning they are constant regions. And identifying the differences for reads in the constant regions is redundant, because there are essentially no changes. So we don't really have to do, for most of these regions, we don't have to do mapping at all. So this was the first solution and the potential issue with that. So let's go over the second solution when remapping reads. So when moving the mapping locations between an old reference genome to a new reference genome, what we don't want to do is that we don't want to do read mapping unnecessarily. And when moving the reads to a new reference genome, we take all the mapped reads and we move the reads that fall either under the constant region or the updated region directly to their corresponding positions in the new reference genome by taking into the deletions and insertions account. So this means that we're not changing anything but their mapping positions based on where these constant and updated regions now exist in the new reference genome. So this is provides a minimal computation overhead to move the reads to a new reference genome. However, this is essentially an inaccurate mapping, because we're missing the reads that fall under the retired region, or we're not mapping reads to a new reference genome, or we're essentially missing the fact that the reads that are under the updated regions could now map to other regions because of these slight changes between two reference genomes. So let me try to illustrate that. So as I already covered, if a particular region is exactly the same between two reference genomes, we can simply move their positions, and then this is a good remap, because we wouldn't assume that the read should map to any other region better than this particular exact matching region. Although it could still exist, still it is unlikely that such a thing will happen. So, but there are also bad remappings. So we label them as cannot remap and bad remap. So in cannot remap is the reads that are falling under the deleted or the retired regions, they cannot be remapped. So we're missing the information there. But there are also some bad remaps. These reads are falling under the updated regions, and there are some differences here. So this means that that particular read was aligned to that particular region in the old reference genome by taking into all the differences between this region in the reference genome and the read into account. But now there are newer differences, meaning the alignment score that we're calculating would have changed if you would align this read to that particular region again. So this would mean that then this read could still map to this region again, or some other region with a better alignment score. But we're missing out that information as well by just simply moving the read to that to this corresponding position in the updated region. So a large portion of the mapping information is then lost or inaccurate by simply moving the reads from constant and update regions to their corresponding positions in the new reference genome. So then let me go over our goal and the key ideas in AirLift. So our goal is to accurately and quickly remap all the reads by either mapping them or moving them. So we're going to choose either of these options, not mapping all the reads or moving all the reads. So we're going to have the chance of picking either mapping or moving from the old reference genome to the new reference genome. So to this end, we propose AirLift. AirLift avoids redundant read mapping for the constant regions, and it quickly identifies and maps the reads that cannot be accurately moved to the new reference genome. So let me go over the key steps in AirLift then. This is the overview of AirLift. So what AirLift does is that AirLift takes all the map reads from the entire region of the old reference genome. It also takes all the unmapped reads, and then it quickly maps them to the new reference genome with a low computation overhead and accurate mapping. So to achieve this, AirLift has two steps. First step is AirLift indexing, which is an offline step. It is done only by just once, whenever there is a new version of the reference genome, to move it from old reference to a new reference genome. And the second step is AirLift mapping, where we map the reads by looking at this indexing information that we generate. So I'll go over the first step, which is the indexing step now. So AirLift indexing step has 8 steps, and the goal is to accurately identify all these 4 regions that can exist between old reference genome and the new reference genome. So I'll now quickly go over all of these 8 steps to illustrate how we're constructing the AirLift index. So the first step that we do in the AirLift indexing is we find exactly matching regions by applying some global alignment between the old reference genome and the new reference genome. So whenever there is an exact matching regions, then we know that these are the constant regions. So for now, we can label them as constant regions. So for all the other regions that are not exactly matching between 2 reference genome, we extract the overlapping k-mers or overlapping seeds. And these seeds are usually of length as they are as long as the read length. For example, if we're using short Illumina reads of length 100, then these seeds again would have the length of 100. So after extracting these seeds that do not align exactly between old and new reference genome, we align them to the new reference genome. And whenever there is an alignment, then we can tell that these 2 regions that have many aligning seeds to each other should be highly similar to each other. Although they are not exactly matching, they are highly similar to each other, so we label them as updated regions because they only incur slight changes between them after the alignment score. And after this step, there are still going to be some regions where the seeds are not going to be aligning in the new reference genome. So for those regions, if the seeds in the old reference genome cannot align anywhere in the new reference genome, then the region that we extracted those seeds should be labeled as the retired region, because apparently that particular region no longer exists in the new reference genome. So similarly, if there are no seeds that are being aligned in the new reference genome, then we can assume that that particular region should be novel, because no seed could be aligned to that particular region. So we label this region as a new region. So we're not over yet. We're not done yet. This is because now that we identified the novel region, the idea is that these novel regions can still be highly similar to some other regions in the old reference genome, meaning we may actually need to consider remapping the reads that are being aligned to these regions that are very similar to the new region, so that we can decide, we can have a second chance to decide whether a read should, for example, stay in the constant region, or if it is highly similar to the new region, should be mapped to that new region, because the alignment score would be much better when aligning that read to this particular new region. So to do that, what we do, again, we generate all these seeds from new reference genome and then align them to the old reference genome. And whenever there's a high similarity, we again identify these regions as updated regions. So with that, like we now accurately identify all constant regions as well as the updated regions along with new and retyped regions. So these are all the steps that we apply in the indexing step, and this essentially gives us a sort of like a lookup table, meaning given a particular position in the old reference genome and given a new reference genome, should that particular position be considered as a constant region, or updated region, or a retyped region, etc. So let's then go over the steps that we do when mapping the reads from an old reference genome to the new one by using this AirLift indexing information. So what we do essentially is we take all the mapped reads in the old reference genome, and then we quickly move the reads that are only in the constant region. So let me do the animation again. So we just move the reads that are in the constant regions, because we know that they are exactly matching in the new reference genome, and they don't have another region that is highly similar to that particular region in the new reference genome, for example, as could happen in the new regions in the new reference genome. So by ensuring that we can accurately move these reads from old reference genome to new reference genome also efficiently, and what we then do is that we remap the reads in the updated regions. So those reads could be again mapped to the same or similar regions, or they could be mapped to the new region, or they could be again mapped to the updated region but some other position in the updated region. And then last, what we do is that we remap the reads in the retyped region to the new reference genome, so that we again give them a second chance to be remapped in the new reference genome. And last, we again map the all unmapped reads to the new reference genome. So by following all of these steps, AirLift fully utilizes all the reads by either moving or remapping them. And AirLift generates an accurate alignment file, a BAM file, that can easily be used in downstream analysis. So with that, I'll go over the evaluation part of our work. So we perform remapping, and our baseline in remapping is fully mapping all the reads, which is the first approach. So mapping the reads from scratch to the new reference genome. And there are also, we compare AirLift to two state-of-the-art works. One is CrossMap, which is a remapper that can generate the alignment files, and also Liftover, which is a remapper that generates only the updated positions. To calculate the accuracy, after remapping, we perform variant calling using AirLift and full mapping. So we cannot use CrossMap or Liftover for variant calling, because they cannot generate BAM files that can work with the downstream analysis, because they cannot either generate a BAM file in the case of Liftover, or with proper cigar strings and other flags, or in the case of CrossMap, it cannot quickly and also accurately modify all the alignment flags such that it won't be a problematic when going over the downstream analysis, for example, marking duplicates and also performing variant calling. So those flags should be accurately handled, so that, for example, the paired and read information would be carried out accurately. The supplementary reads The flag regarding supplementary reads also would be handled accurately, etc. So those flags are also handled in AirLift accurately, such that we can use the resulting BAM file in the variant calling with no issues. So we use various data sets. For example, human genome, we have multiple reference genomes. The oldest HG16 and newest in our case is HG38. We use a worm genome again, and also yeast. So this figure shows the performance result compared to full mapping, cross map, AirLift, and liftover. On the y-axis, we have the execution time. On the x-axis, we have the old reference genome information and the new reference genome information. So this means that, for example, in this particular region, we can tell that we generate the results by moving the reads from HG16 to HG38. And in this particular region, we can tell that we generated the results by moving the reads from HG19 to HG38 again. So by looking at these figures, what we see is that AirLift provides on average 2.6 to 6.7x speed up compared to the full mapping. But of course, it is slower than cross map and liftover. This is simply because AirLift provides a more comprehensive mapping. Then it leads to longer execution times than cross map and liftover. We also show the peak memory usage. Here we have the peak memory usage on the y-axis, and the x-axis is similar to what I've shown in the earlier slide. Again, we compare against cross map, liftover, and also full mapping. So what we observe is that the peak memory usage is similar to full mapping. Still, the peak memory usage of AirLift is much more higher than cross map and liftover due to the similar reasons, which is performing more comprehensive mapping, which eventually leads to more accurate read mapping. So then let's look at the read mapping accuracy results after we perform variant calling from these read mappings. So we report precision and recall values over here. So the leftmost value would be the precision, and the rightmost will be the recall value. And we compare our results to ground truth variant calling results. We do this for both our baseline, which is full mapping, which means that we're essentially mapping all the reads directed to HG38, and then we're calling the variants, and then we're identifying the accuracy of SNPs and indels by calculating their precision and recall values. And we do the same for AirLift by moving the reads from HG16 to 38, again, by using all the older versions of the human genome. And we generate, again, the accuracy results by looking at the ground truth values. So we also compare the variant calling results that the AirLift generates with the variant calling results that the full mapping generates. We again generate the accuracy results for that. And for all other data sets, which are the worm and the yeast data sets, we don't have a ground truth variant calling for that. But for those, we compare our variant calling results that AirLift generates with the full mapping variant calling. But essentially what we see is that AirLift provides a comparable accuracy to full mapping without a significant performance cost. So we see this by looking at, essentially by looking at these results. Here, the SNP and the indel accuracy of full mapping is around 99.54% and 81.31%. And here, especially by looking at the SNP results, the accuracy of AirLift is very close to the accuracy of full mapping. And the AirLift can actually generate very similar accuracy results without even fully mapping the reads from scratch by providing these significant performance improvements. So with that, let me conclude. Remapping to a new reference genome is either costly in the case of full mapping or inaccurate in the case of moving the mapping positions. And our goal in this work is to accurately and quickly remap all the reads by either moving the reads or mapping them from the old reference genome to the new reference genome. And AirLift has two steps to achieve this. First is AirLift indexing, which accurately categorizes and labels each region in the old reference genome compared to the new one. And in AirLift remapping, we remap a read to a new reference genome, or we quickly move its position based on the information that we generate in the AirLift index. So AirLift consistently outperforms full mapping. So it provides 2.6x to 6.7x speed up over full mapping. And AirLift identifies SNPs and indels with precision and recall very similar to the full mapping accuracy. So AirLift was presented again a few months ago in APBC conference, and is also invited to be accepted to IEEE TCCB. So you can read the preprint of AirLift by using this QR code. So the source code of the AirLift is also available on our GitHub page. So you can also reach the source code using this QR code. So this was AirLift.